Math 1314, Chapter 6, Matrices and Determinants. Section 1, Matrix Solutions to Linear Systems. Video 6, What could go wrong? And not really wrong, but just different, because the presumption, as was stated in the previous video, is that we're going to get to a solution that's unique. In other words, a unique solution exists to a system of equations. But as we've already seen in some examples back from Chapter 5, a system of equations can have no solution, and a system of equations can actually have an infinite number of solutions. So when do those arise when using matrices to solve a system, and how do we conclude those problems? Well, we're going to take a look at both examples. The first thing that can happen is that you get a row of zeros on the left of the bar and a zero on the right of the bar. In other words, you get zeros all the way across. Now, this is going to happen. It's destined to happen. There's absolutely nothing you can do to control it. It's either going to happen or it's not going to happen. Now, why is this a problem? Because if we try to turn this back into a system of equations, the top equation would say x minus 4z is equal to 6. And the second equation would say y plus 3z is equal to negative 1. But what would the bottom equation say? The bottom equation would say 0 equals 0, which, number one, is clearly true, and number two contributes absolutely nothing to the solution because it says nothing about x, y, or z. So it's pretty much a useless equation, and we could just throw it away. But how do we continue to solve? Well, without getting too deep into a topic called linear algebra, whenever you have more variables than equations, you cannot have a unique solution, but you can describe the solutions. How can we describe the solutions? Well, what you do is you take the variable that did not have its own equation, and in this case, the z, and it's what's called a free variable. In other words, the column where we should have had z equal to something down here, the z can be free to be whatever. So z is what's called a free variable. Its value is free to be whatever it wants. However, once you choose a value for z, it determines the values for x and y. Because if you can imagine substituting a value here and here for whatever we choose for z, then we can solve for x and y. So if z is free and x and y depend on the z, then all we have to do is solve each equation for in terms of z. In other words, solve for the x, solve for the y. Well, those would both be pretty easy to do. If we solve the first equation, we get x equals 4z plus 6. Just add the 4z to the other side. If we solve the second equation, we get y equals negative 3z minus 1. And so that means our solution is the set of all ordered pairs that look like this. X is going to equal 4z plus 6. Y is equal to negative 3z minus 1. And z can equal anything it wants. So we can say z is any real number. So give me a value for z. I'll stick it in there everywhere I see it, figure out what x and y equal. Boom, there's a solution. And I can do that for every possible value of z. So anytime you get a complete row of zeros on the left of the bar, 0 on the right of the bar, that means you have a free variable, a variable whose value is free to be whatever it wants because everything else depends on it. So you solve for those other variables in terms of the free variable. In this case, solve for x and y in terms of z. And then you write a generic ordered triple, x comma y comma z, except you write what x equals, y equals, and then the letter z, and then you state that z is any real number. But what else can go wrong? Well, the other thing that can go wrong is when you have a row of zeros on the left of the bar and a non-zero number on the right. Now, what happens when this occurs? Well, the top equations are still the same. X minus 4z is equal to 6, and y plus 3z is equal to negative 1. But what does the bottom row say now? What does the bottom row say? Well, the left says 0x, 0y, and 0z, so 0 is equal to 5. Wait, what? 0 is equal to 5. That's impossible. 0 cannot equal 5. And when this happens, what you're saying is, I need something to be true that's impossible. That will never be true. Whenever this happens, when you have a row of zeros on the left of a bar and a non-zero number on the right of the bar, the conclusion is that the system has no solution. Because you're asking an equation to do something that's impossible. You're asking for 0 to equal 5, which clearly won't happen. So to summarize the two things that can go wrong or different, one row gets completely zeroed out from left to right. That's all right. That means the variable that should have been represented in that corresponding column, third row, third column, is a free variable. You solve for x and y in terms of that. You solve for the other variables in terms of the free variable, and your solution is a little bit more generic because you write something like this. If I can get it to highlight. And the other thing that can go wrong, and this is a quicker conclusion, is if a whole row is zeroed out on the left side of the bar, but not on the right side of the bar. If this happens, then you get an impossible equation, an equation with no solution, and therefore the system has no solution.